So guys, yesterday we went through the fuzzing script in which I will just refresh your memories. So, so okay. So we went through the fuzzer script. If you can recall, what we did was that we tried to fuzz the application by sending character A, and we found out that after how many bytes, basically the application actually crashes, right? So if you can recall, we found out after 2700 bytes, just put it as a comment. After 2700 bytes, the application actually crashes. Then we actually wanted to find the offset because we were actually not sure exactly, is it less than 2700 bytes or more than 2700 bytes? So if you remember, we basically used this script to create a pattern. And then we used the second script, which was pattern finder, in which we simply generated the pattern by using this script pattern underscore create minus L and 2700. So we got 2700 bytes of this pattern. And then we basically again overran the buffer and we noted the memory, the value of the instruction pointer EIP, which basically we got 396 94438. Right, so we completed this step, and then by using this particular script, we found out exactly what is the offset. So I will just run this step one more time. So we use this script and the value of the instruction pointer EIP with minus Q option, and we found out that exactly after 2606 bytes, the instruction pointer starts, the EIP actually starts, right? So this is the step that we did yesterday. Okay. And we also know that the instruction pointer is actually 4 bytes. So which basically means that if we add, if this is the number of alphabets, if we send it to the application with A, and then we actually reach the instruction pointer. Now, what we wanted to do was that eventually that this instruction pointer, we want to actually replace it, or this, because this instruction pointer actually refers to a memory address, right? So that memory address we want to find out and then replace it with, the address of our shell code that we are going to create. I think step number 3, we did this step as well in order to find out if exactly after 2606 bytes the instruction pointer will start. So if you can recall, the next script that we did was we basically, it's a simple script. We basically just sent 2606 A characters, and then we sent 4 B characters. So if you want to write it like this, it's fine. If you want to write like I did yesterday, I put 4 times B. So it's actually the same thing. I'm going to repeat this step one more time just to pick up from where we left yesterday. So I will run this script again to show you that the instruction pointer should be replaced by B. If it is exactly replaced by B, 4 bytes, uh, which basically means that the offset that we found out 2606 is actually correct. So I'm going to use this override script one more time. My application is running on the Windows. Um, so let's just go through the Kali Linux again. So CD desktop buffer overflow. So I'm going to run this script to overwrite the EIP with these. Okay. So you can see here overwriting the EIP with exactly with B. So when we come here, you can see the value of the EIP. It's basically 42, 42, 42, 42. So each of these 1 byte, 42 represents the character B, and A is represented by 41, right? So now we know by running this particular script that the offset that we found out is actually right, which is 2606 bytes, right? So I have reperformed this step, so I need to go back once more to close down this immunity debugger, because once we crash the application, overrun the application, we need to restart it. Okay, so this has started again. I will run the immunity debugger one more time and attach it to the SL made, right? And then play. All right. Now, there's one more step that we have to do before we try to find out the, uh, you know, jump ESP memory location and then replace it and send it to EIP. The step that we want to do next is actually to find out the bad characters. So the applications, different applications, they do not accept some characters, which we call as the bad characters. So we need to find out, and every application has different bad characters, okay? So we need to find out what are those bad characters that this particular application does not actually accept. And we will have to remove them um, from our shell code, because if we don't remove those bad characters, then our exploit may not work, right? So how do we do that? How do we find out the bad characters? So if you go to the platform, um, it's actually given as character char test string, and these are all the characters which are given in the hexadecimal numbers, right? So what it does is that when you use these characters, it is going to send it to the application, and we are going to verify or check. It's a tedious job actually. For this particular demo, we know which bad characters are there. But if you are doing it on some other application, you may have to go one by one to find out what exactly are the bad characters that the application does not accept. Right, so the first thing you need to do is you will copy this, and let me just open the script for you. So again, nothing is changing actually here. What we just do here is that I just define a variable bad character equal to, and then I copied it from the platform, okay? So as you can see, \x0102030405, and after 09 actually originally has to be, because I removed it, So 0A was one of the bad characters. I'm just going to put it back. 0A. Let's copy it again. I think it's better. I will copy it from the platform. Okay. Control C. The reason I'm replacing it is because I already uh, yeah, because I already deleted those bad characters from the script, right? So that's why. So it's not okay. So this is what I've copied from the platform. So it has all the bad, all the you know characters x01 in hexadecimal 01, 02, 03, 04, 05, 06, 07, 08, 09. And then we have A, B, C, D, E, F, then 10, 11, 12, and so on. It reaches F, F, the last hexadecimal. Okay. Now, what I'm trying to do here is that I'm sending the alphabet A, and we found the offset, which is 2606, plus I'm sending 4 Bs, and then I'm sending this bad characters that are basically here, and then we will find out which bad characters are this application does not accept, right? So I'm just going to save the script. Okay. And let me go back to the terminal. So let me just double check my application is running. Okay. So you can see at the bottom on the bottom right side that the application is running. Now, what I need to do is that I will run this script. Python 4. This is the fourth script that I'm running in order to find out the bad characters. Right, so I've sent this, and then I go back to the Windows. Okay, now if you see here, it actually, we successfully overran the buffer. The instruction pointer reached 42222, and then we sent the bad characters. Now, let's just go to ESP here and right click and follow in the dump. So if you see here, follow in the dump, you can see it starts with 01, okay, 02, 03. Let me just show you as well in the other, what we sent. So 01, 02, 03, 04. So I'm going to check one by one till 09 and see that all of them, they basically were accepted by the application or not. So 01, 02, 03, 04, 05, 06, 07, 08, 09. Now till 09, everything is fine. All these characters were accepted. The next one that you see here is 29, but if I go back to the script, after 09, /0A is basically not there, missing, which basically means that this is one of the bad characters that the application does not accept /0A. Okay, so this is the first one that we identified. So I'm just going to take a note here. Okay, I will delete the \x0a is not accepted by the application. So this is the first bad character. Number two. So what I'm going to do in this script is, first of all, I need to go back, stop the Immunity debugger, stop the application, start it all over again, right click and run the Immunity debugger, attach the program, SL mail, run it through the debugger, and play. Okay. Now I go back to my Kali Linux and I remove this bad character, which was X0A, because the application doesn't accept it. So I'm going to remove it, \0A. So I have removed it, and the next one is 0B, 0C, 0D, 0E, and so on, right? So I'm going to save it, and I'm going to run this script one more time in order to find out that if I have, removed 0A, then the next one should be 0B, whether it's coming is being accepted or not, right? So I'm going to run it again. When I come back here and I go to the ESP and follow it in the dump. Okay, so let's start again. 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8, 0, 9. So when I removed A, now you can see that 0B is being accepted, 0C is being accepted, and 0D is not accepted. So what it means is that in this, 0D is also not accepted, right? So the second bad character that we just found out is /0D /x0. D is the second bad character that will not accept. Not going to repeat the same process again. What you need to do next is to remove this as well. So 0D is gone. And then you will run it one more time. Now for this particular application, we know that the two bad characters in this application are actually 0A and 0D. One more that you must include in almost all the applications is basically null bytes. So X00, you have to add it as well, which is, you might have gone through in many, labs or maybe some discussions as well, that the null byte is also listed as a bad characters. Okay, so these are the three bad characters for this application, which we have found out. Why do we need that? I will just tell you shortly, but you have to keep note of them. All right, so the next important step is that we need to find out the jump ESP. Jump ESP function basically means that it, when the application is running, if you can find the jump ESP function where it is located in the memory, it actually, whatever address you have at the jump ESP, this will force when we have the EIP. So the instruction pointer still, we did not point it to anything. We are just overwriting it. If you remember, we are just overwriting it with B's, right? 4 times B. However, if I put here the memory address of the jump ESP, okay, if I make like this, that EIP is equal to the memory address of jump ESP function, then what I can do is that I will actually force the application to go back on the top of the stack where we will have our payload. Once it goes to this particular address, our payload will get executed, right? So what we are interested in finding out is that we want to find out where exactly in the memory we have this jump instruction, right? Now, luckily, this step is very easy. It doesn't really require any, uh, what do you call that, script. Uh, the script that is actually required is actually called Mona script. Now, if you have downloaded this virtual machine, which is on the platform, this Mona script has already been added to the immunity debugger, so you don't need to include it. However, if you are running a new virtual machine, Windows 7 machine, and you have installed the immunity debugger, then you will not find this script. So in that case, if you are doing that, you will have to download this script from the GitHub and place it into the scripts folder of the immunity debugger. Okay, I will just show you. Sorry, not here. If I go back to the Windows, I'm just saying, if you're not using the virtual machine that is on the platform, you need to download the Mona script and place it inside the immunity debugger folder. So let me just open it for you and show you where exactly you will copy that script. So program files, immunity debugger, py commands. You can see this directory. And here you can see there is a mona.py script that was later added. It is not built in available when you install it. Now, where you can find this mona.py script, you can just simply Google it and you will find it, okay? Right, like I said, if you're using the virtual machine downloaded from the platform, you don't need that, okay? So mona.py script, GitHub. So you can download it from here. Okay, there is your mona.py. You will download it and copy it into the directory of py commands, and then it will start working for you. Clear? Guys, any questions so far? So I'm recording, yeah. So far clear, guys?
Yes, Dr. Hassan.
Now the next step is, I mean, we didn't do that step still. I'm going to close this script. We don't need that right now. Okay, so I need to go back and restart the application like we are doing it every time. So I'm going to stop the immunity debugger, stop the application, start it again. All right. Right click, run as administrator, yes. File, attach. You'll get good at it. But you may have to practice like many times. All right, so I'll run the application and let's just find out what is the memory location of this jump instruction. Jump ESP also we call it. So you will copy this command and I have shared this text file with you yesterday. So you just simply need to copy. And by the way, the hexadecimal value for jump ESP is FFE4. So that's why you can see it here, minus S X FF X E4 in the hexadecimal. So this \X means hexadecimal. Okay, so I will copy it here at the bottom. As you can see here, the application is running and I will press enter. And let's wait for some time. Now the jump ESP is actually, this function might be in more than one places in the memory. So this is like an instruction, okay? All the programs All the softwares, they're basically a sequence of instructions. So one of those instructions is jump ESP, and we are looking for where in the memory is this jump ESP instruction. And then we are going to use that memory to replace it into the ESP that pointed to that particular memory, which will actually take it to the top of the stack. We will have our payload, and the payload will get executed. Okay. So now, if you see here, um, as you can see, the number of pointers of type \x ff \e4 is 19. We need the one among all of them. So we'll take the first one, which is, as you can see it here, it is 0x into 5f 4a 35 8f. So this is basically the memory location, first memory location. This is another memory location. This is another. Also, you have to make sure that the values here, like ASLR is false, so rebase is false. All these values are false, most of them, which basically means that this is not a protected function, so or not a protected memory location. So this is ideal for us. So if you get more than one, and if you find out that the first one is actually protected, which means ASLR is true, for example, or rebase is true, so you move on to the next memory location that you have, which is basically having these values as false, right? So right now we have 5f 4a 35 8f as the memory location. So I'm just going to close it. I already noted it down in the notepad file. So I actually noted more than one, so I'm going to just erase them in order to avoid the confusion. Okay, so I will delete this, and we don't need this. Now, when we find out the memory location of the jump ESP, what you have to do is that you have to rewrite in the reverse order. Okay, so starting with the 8f hexadecimal byte, then 35, then 4a, and then 5f. The reason why I have done it is because just a minute. The reason why we have done it is because the next script that we are going to do that will consist of our payload. The memory should be written in this order, in the reverse order, the memory location, right? So it will be something like this: \x 8f \x35 \x 4a \x 5f, right? So it has to be written in this order. If I'm not wrong, if I'm not missing anything. Okay. So we found out the jump. Okay, another way, if you want to verify or confirm that this memory location is actually correct and not wrong, what you can do is just copy this memory location that we found out. So I'm just confirming it, okay? And I will go to the application, and if you see here this black arrow on the top, just here, click this one. This is basically a breakpoint. I will paste this address that I found out and then press OK. Let me do it one more time and press OK. Now, maybe the second time, usually it works like this. So now if you see here on the top in the CPU registers, you can see this memory address that I just copied into the breakpoint. So 5f4a35 8f. This is FFE4, which is basically a jump ESP instruction. So which basically means that the address that we found out is actually correct. Okay. Now the EIP, the next instruction pointer, we will have to point it to this address. 5F4A358F, which basically means that once we overrun the application with 2606 A's, then the next instruction is telling the system or the processor to go to this memory location, which is basically a jump ESP. When it goes to jump ESP and the memory location 5F4A358F, it basically goes back to the top of the stack where we will have our payload, which gets executed. Is this clear, guys? Okay. Now coming back to creating the payload. So MSF Venom, you are very much familiar with it, so I don't think there's any explanation required for this. So I will just paste it here. So I'm using the payload, which is Windows shell underscore reverse underscore TCP lhost is equal to the IP address of the Kali Linux, right? So 192.1.157, I think. Let me just double check this. Okay, so 1.157. And the L port is 4445. You can put any port number 1, 2, 3, 4, 1000, 2000, 443, whatever you like. So the L host is 192.168. Sorry, not 268, 168. 1.157, and then the L port is 4445. The format here is PY. Okay. Actually, the format you can actually put Python as well. You can put C as well. It depends. I'll come back to that later, but for now I'm using the Python script py. And then we have the -b are the bad characters. So this is where you basically are going to generate a shell code, avoiding the bad characters in the shell code. This is why we took note of these 3 bad characters, which the application does not accept. First one is the null bytes, the 0A and then 0D, right? So -b for the bad characters. These are the 3 bad characters. And -e is x86 Shikata underscore Ganai. Forgot what is the E. We can get it from help as well. But this is basically kind of an encoder, you can say. Shikata underscore Ganai. Previously, I have used it long time back actually for antivirus evasion, but here it's not really doing the evasion, but it will generate the shell code. Okay, so I hope this command is clear. So the payload that we are using is Windows shell reverse TCP. You want to do Metapredator, you can put Metapredator, whatever you like. Okay, but for Metapredator, you need to then run the exploit and all that. So if I'm using a Windows shell, I can actually run a netcat and listening on this particular port 4445, and then it will start working. Get connected to the netcat. Okay, let's press enter and see what happens. So generating the shell code. At the same time, what I can do is that I can also start a netcat listener. So netcat minus NLVP 4445 listening on this port. So when I send the exploit, the next one, So now you can see basically what this command has done is that it has actually generated a shell code which contains this particular payload with this L host, with this L port, plus it is avoiding all the bad characters. All right. And what you see here is the shell code. You need to copy it. And at the same time, like I said, where is it? I started the netcat listener as well. So many terminals open. Let me close it down. Sorry guys, I have too many terminals open, so I'm just closing them down. Okay, so I have the listener running. I have the shell code. There's one last step that we need to do uh, to exploit it, okay? Guys, just give me 1 minute. 5 minutes, in fact. I'll just stop the share and I will come back, okay? Oh, sorry. Yes. Okay. Share this screen back with you. Okay, so before I uh, start the script, I need to close down the immunity debugger, stop it. Okay. Start again. Run as administrator and file attach. You'll take some time to actually learn this, okay, guys? So don't worry if you're not able to go through it from the first attempt. You will have to spend a lot of time. Okay. Now coming back to the Kali Linux. So since I have created this shell code, we'll copy it and actually the shell code that you see here, it's the format is C, so that's why you cannot see B here. I'll show you the other script, I think. It's on the desktop. I mean, like tens of them. had a lot of issues. Okay. Now, what do you see here is that I'm going to replace this with the shell code that I just generated. Control V. Okay. So now you have a variable buffer the BUF, which contains the shell code. I'm going to share this with you, okay? This whole script. And then we have another variable characters. So we want to send 2606 times A. For jump ESP, the small b represents the byte, okay? All the b here represents the byte, so converting the string into byte. This is basically the memory address. So what we are trying to do here is that we are declaring a new variable and we say, okay, this jump ESP. Actually, we don't need to declare all these variables. I can actually write them directly here in this place. But let's just go with the script for now. So the jump ESP is the memory location. Then we need to include some NOPs. NOPs means no operations. And this backslash x90 that you see here, it actually means if there are any spaces. So when it jumps back to the top of the stack and goes through it, if there are any spaces, so to be on the safe side, we put 16 here. You can put 20 as well. You can put 10, it's up to you, but no less than 10. So the recommended is at least 16. So if there are any spaces, it is going to ignore them. NOPS means no operation. So it is not going, oh, sorry, x90 backslash x90 means no operation. Don't do anything. And then reach this particular payload. So let me just show you now the payload that we are sending. So the payload is equal to the alphabets, the characters here, as you can see, okay, chars, which is basically A times, sorry, 2606 bytes of A's plus the jump ESP means the memory location of the jump ESP. So it will go here and jump to the top of the stack. If there are any spaces, ignore them and then execute this shell code, which is BUF, which is basically our shell code that we just generated, right? And then here you can see the rest of the stuff is actually the same, the IP address of the target, the port number, and we are sending the payload. Now, the other script that I had is it's quite similar and quite simple, will make more sense to you. The only difference here is that you don't see BB written here because I use the format in the same script as -C. So instead of using the Python, I used the C format, and this is much easier for you to understand. So what I'm going to do is I'm going to send this payload, I'm calling it attack, is equal to A times 2606 plus the memory address of the jump ESP written in the reverse order, plus 16 no operations. If there are any spaces, ignore them. And then plus BUF basically is the variable that we have. So I can run either of these scripts. The difference is that here I'm using the shellcode that I generated as the C, and the other one was the Python. Okay. So if I have to use that, then the only thing, if I'm using this particular script, let me use this script. I'm more comfortable by using this particular script. Okay. So, or I can use any of them. Okay. So let me just open a new terminal. cd desktop. So Python, this is the last script. Exploit.py. So as it says, exploiting, which means that I used this particular script. Okay, so I will just repeat one more time. Overwriting with A, sending exactly 2606 bytes, then pointing the EIP to the memory location of jump ESP, which is written here. This is the memory location, plus the NOPs. So the NOPs means that if there are spaces, ignore them, and plus the buffer BUF, which is our shellcode, right? So after running this, let me go and check. So as you can see here, it was running on port 4445, and the shell code that we generated was basically to give you a shell, not a meterpreter session. If you do the meterpreter, it will not work because I'm running netcat. Okay, so it's only listing on this particular port. If you want to use the meterpreter, you will have to run metasploit and then use the exploit that was multi-handler, and then you have to do a lot of stuff. So to keep it simple, we just run the netcat -nlvp start listing on port 4445, and when we send this, it basically gives you the shell, right? So this is the end of the lab. uh, it will take you some time to actually go through it, and you know but the more you practice, I will recommend those who are really interested in offensive security track. This is one of the major tasks that you have to do in OSCP. I don't know if they are still doing it, the manual buffer overflow attack, but I'm sure they will have this. So because I went through OSCP long time back. The best track for penetration testing is the offensive security track, okay? Not the CEH track, but the offensive security track. So if you Google offensive security, you will find OSCP, OSWP, OSEP, and OSWE. So they have a full track. So you don't give any multiple choice exams there. You basically have to practically hack their machines, and then you get the certification. And it's really difficult. It will take you at least maybe 3 to 4 months to get the first certification, which is the OSCP, Offensive Security Certified Professional, if they haven't changed the name also. And they, with the passage of time, they change their machines. They make the difficulty level also different. So I don't know what is going on currently, but that is what you should be looking for. And this is one of the challenges in the OSCP, that you have to do the manual buffer overflow attack on some application. Not the same application, some other one. The process is going to be same. Remember, every application, whatever it is running, the process is same. The only things that you may have to do is to find out the offset, to find out where is the EIP, the instruction pointer, the next instruction pointer. Maybe the bad characters are different in different, not maybe, for sure, the bad characters are different in different applications. And then you just have to find out the jump ESP location in the memory. Okay. So with this, we have completed the buffer overflow. You can work on it. I'm not going to do another lab today because I know this will take you time. Even if you have done it yesterday, you may have to repeat those steps as well. Okay. So I'm not going to share all the scripts with you. The last probably that I did, I'm going to share it with you guys. If you have any problems, I cannot troubleshoot the problems for you. You will have to find your own way out. Okay. So that's it from my side. Stop sharing the screen. and I will stop the recording.